I'm Eric Reinecke. I am a video engineer on the encoding team at Netflix. I'm here to talk about edit intelligence in production pipelines. So who are we and what do we do? On the encoding team, we are people who make sure there are streams that are ready to view at whatever quality you need, given whatever connection you have, and have them still look great. We're also the group that, we have the group within our greater team that works on the VMAF perceptual video metric, which tells you how good your video looks based on how a human sees it rather than how a computer sees it. We spearhead development of new codecs. AV1 is a big focus for that team at the moment. We're working with media asset analysis and metadata management. So you may have seen a tech blog talking about identifying text within video streams. And also there's a certain thing we have called NMDB, which lets us do spatial time-based storage of database things. And then finally, my group, Video Engineering, we work on a lot of workflow tools that apply the sort of lower level tech things to more specific workflows. So among the things that we've done a lot of work with have been developing the IMF standard, and then also a lot of help in rolling out the Bandersnatch title, which required a lot of innovation on the encoding tech front. So I love editorial. It's the place where film comes together. It's said a film is written 3 times. The first time is on the page when the screenwriter commits it to paper. The second time is when the actors and the director on set interpret that in front of a camera, and that gets recorded to film or more likely a card. And finally is in the edit bay. The edit bay is where the film has its final rewrite. Characters it can be decided whether a character lives or dies in a movie in the edit room. The editor, in some weird way, in the context of the story, kind of gets to be God. And I think there are so many movies that are found in the edit, regardless of what happened before, you can make it happen there. So I believe that if we create timeline-aware pipelines, we can use that information from the edit to help all the people working on the production focus their effort better on how they can make the movie and less on doing things that won't impact the final output. So today what I'm going to talk about is what timeline-aware pipelines actually means. And then I'll talk about some background on ways for making timeline-aware pipelines that we've used in the past. And finally, I'm going to talk about OpenTimelineIO, which is my favorite way to make timeline-aware pipelines, but it's a new kid on the block, kind of. OK. So if you're a filmmaker, you want to look at any given moment, or any given moment in the process of making your film. You want to look at what your movie would be if you shipped it right now. So you can imagine if you hit the go button at some point, it would just be a 2-hour movie of pages of the screenplay flipping by, right? So this is an easy thing to know when you're at the pitch stage, because it's just someone with their elevator pitch. And it's easy to know when you're at this stage of there's a tile in your Netflix row that you hit play on and you see the movie, right? But what about this in-between zone? How do we know what the movie is at any given moment? The process of production is really about a crew that are making all these micro decisions on a day-to-day basis all the time. And in order to do that, they have a lot of questions they want answered, right? They need to know, where can I be focusing my time in this exact second that's going to have the greatest positive impact on making this movie successful? So they need the information to drive that. And I think edit data represents these sort of tea leaves. And if we can figure out how to look at, interpret, and communicate that data out, it'll help answer certainly all the questions on the screen right now. A more concrete example of this is or a way we're using this at Netflix right now, is the trailer creation process. So what we do is we start with a bunch of MPEG-4 proxies of full episodes of a show. Those are delivered to an editor who assembles them and makes something that's going to make you know that this title will bring you joy when you watch it. And then what they finally do is they use that assembly to drive, or they use that edit decision set to drive how they get the high-res content. So if we look right here, it's not important what the text is. That sort of represents the durations of all these episodes that they might start with for making this 60-second trailer. So each one of those is a 22-minute episode worth of video, right? And when you look at this, which is much more sparse, those blue areas are actually the areas within those specific episodes that are actually used in the output 60-second trailer. So you can see that there is a vast majority of that material that doesn't actually make it into this specific product. So the question is, given this knowledge, how do we translate that into a quality of life improvement for our assistant editors so that they can be happier and they can make better trailers and share with the world the amazing content we're making? And this is an engineering meetup. I think we should go with some numbers. So from that specific example I pulled, of the 4 hours of source content, only 59 seconds are used in the final product. So that represents about 0.4% of the source material that they're using. And what that means is 9 megabytes out of that 2.44 gigabyte worth of MP4 proxies is what makes it in. And finally, when you get to that online conform process where they got to pull this all into Premiere and make the final output product, that's only 1.3 gigabytes of 388.2 gigabytes of masters. So because we know exactly what those ranges were, we can pull only the bytes that map to the frames that the editor uses. By doing that, we take the assistant editor's job of doing that online conform and gain that original material from 52 minutes to 11 seconds worth of download time at a gigabit a second, right? So this is a big impact to be able to create that time in the day where someone can go back, they can spend more time pushing closer and closer to their deadline to make sure they're plussing out the trailer that much more. So when you talk about dealing with full-length content production, right? How does this sort of intelligence map when you're dealing with camera original files, which are even larger? You're talking, 220 megabyte per second data rates. And currently, there's some productions that shoot 4 to 7 terabytes a day worth of camera originals. That's a lot of content. But when you start to think about it, in the final edit, their shoot ratios are usually 10, 20, 50, even 100 to 1 hours they shoot versus hours they shoot to 1 hour that ends up in the final content, right? So that means that out of this 4 to 7 terabytes a day, maybe only 140 gigabytes of that are actually going to be needed to make the final movie. So when you're moving that much data around the world at gigabit speeds, you can go from 15 hours per day of material shot to 22 minutes per day of material shot. And this can be the difference between whether or not you're able to actually finish the show on time or not. So this stuff is very important to us. Given that we know EDLs are useful and can give us all this intelligence about what's being used in the timeline, how do we get this? How do we move this information around? So there's some options currently floating around. Sort of the most ubiquitous one is the CMX 3600 format. This roots back to about 1971. It started with the CMX 600 video assembler. You would do your offline edit in there, and then you would output an sort of a flavor of the CMX EDL onto paper tape, feed that into a teletype machine, where then your CMX 200 could drive a 2-inch tape machine to do your online edit. The earliest CMX EDL description document I could find described how the bytes would be laid out and what those bytes would say on floppy disks. And that was from about 1988. And then SMPTE 258M, which standardized a lot of what more or less is what we know as the CMX 3600 EDL, came on the scene about 1993. So has anyone in here ever written a parser for an EDL format? Show of hands. I have a few times. OK, well. Oh, we got one. OK, CMX EDLs? Yeah, OK. So I don't know if you read the SMPTE 258M spec, but did you make sure you implemented the wait that stops auto-assembly and waits for the editor to give user input, or the bell that sounds an audible bell on the machine? Yeah, I always miss that in my own implementations, too. So when you read the specs about this stuff, what it really is it's about this robot driving a tape machine, and what are the instructions we can give it to do that, which, to its credit, that works pretty well, actually. And I think because of the nature of a pilot driving an auto-assembly machine that is this tape robot, they decide to make the format pretty human readable. So if we look at a CMX EDL, it breaks down to essentially be a tab delimited text. And when you get into it, you have this side, which tells you your time range to select from your source tape. And you have this, which tells you your destination time range to record on your output tape. It's pretty simple. And the readability, I think, is why CMX has been so prolific, because just about everything reads it because it's been around for a while. And any engineer picks up this thing and says, I can write a parser for that. But what happens if you start dealing with more complex timelines that have some complexity? Let's go to my new favorite Twitter hashtag, which is Timeline Tuesday. Let's zoom in. It's not going to help you understand it any better. But this is an actual editor's timeline from a movie they were making. So that's not going to work so well on a flat file. What options do we have to move this around a little bit better? Enter AAF. AAF's a file format that Avid has adopted. It is designated as being for the interchange of audio-visual material and associated metadata. It basically breaks down to a highly structured way to move fairly arbitrary data around. It's a binary format with a rich object structure, and then at some point later, they layered on the edit protocol, which describes how you can actually assemble the essence within it. And actually, MXF is a sort of offshoot from AAF. It allows you to embed the media essences, which is kind of useful, but if you're just trying to understand the edit and you don't care about the essences specifically, that can be a bit heavy to move around. Avid, one of the main NLE companies, has adopted AAF as this interchange format, and sparse other vendors have as well. It's fairly around. So this seems like a pretty good solution, right? Well, there's complexities. The data model within it isn't incredibly approachable, especially when you talk about people like pipeline TDs who want to throw some Python at the problem. The data model also doesn't exactly match how humans tend to think about edit timelines. And it's a little hard to get started working with. It's a big pile of C++ code. The build tool chain isn't exactly clear on all that. It's just not the most approachable format. So I think pipeline adoption of this has been low because it's so hard to wrap your head around it. And the other issue is that the edit protocol isn't consistently implemented by all the NLE vendors. Well, OK, maybe there's something else. There's Final Cut. It has an XML format. And in 2003, Apple actually published this and spelled out how it all works and put a schema out there. And a lot of tools have actually adopted the Final Cut XML format for importers and exporters in an ad hoc sort of way. And it contains structured data similar to how people think about timelines. So it might be a little hard to read, but you can see there's a sequence, and the sequence has a name, and under it has media, and in the video media section it has a track, and tracks have clips, and clips have transitions. That all kind of matches how you think about it. This is pretty good, right? Well, there's an issue with this one as well, because you see there's Final Cut 7 and Final Cut Pro 10, and anyone who's worked with these two packages knows that it was a very fundamental shift. So what that means is that the type of XML that is implemented is very different between these two packages, and knowing which format, which editorial packages are using can be pretty tough. So you end up having to double implement everything. Also, in Final Cut 7, the structured metadata story isn't very good. There's not a great way or a uniform way to hand arbitrary metadata around that might help your production pipeline. So what you end up with in your sort of workflow landscape of all your tools you're trying to integrate together in your pipeline is that you have interchange formats that all have slightly different flavors of each other, and you're always translating between one and another and trying to conform to find something that's going to work with a specific tool. So if you wanted to support the whole landscape, you're going to end up writing 4 or 5 edit parsers, and you'll just spend all your time refining those over time. And when you're working in a production pipeline, it's really important that you can have this good understanding of being able to inspect those timelines, modify them, and pass them on to packages. So you don't have to write parsers, but you have to write writers that will work with those applications. So enter OpenTimelineIO. Full disclosure, I'm a contributor to OpenTimelineIO, so I have biases about it. But OpenTimelineIO is an open source API and interchange format for editorial timeline information. So if we go look at it, when I look at OpenTimelineIO, I like to talk about it as being sort of 3 things, right? There is an API that defines an editorial data model and functionality for working with that editorial data model. There is the interchange format that lets you serialize to a file, communicate between applications. And then finally, there's a collection of adapters that import from other editorial formats and can export to other editorial formats. So you can get in and out of that data model. So wait, Eric, hold on a second. Didn't you tell me that there's already 3 formats? So this is a slide I stole from Stefan, who's one of the maintainers of OpenTimelineIO. And I was talking with a vendor at one point about OpenTimelineIO, and they stopped me so they could pull this up and show it to me at one point. So what is it that OpenTimelineIO is doing that's materially different? Well, if you think about timelines, this is another slide I've stolen from Stefan. He likes to use this printer analogy that there's this continuum between the very simplest ones that are easy to understand, but they're not incredibly powerful. And then there's the complex ones that do everything. They can staple, they can fax, they can print even, but they're just a little too much to maintain, and they're too heavyweight for most of what you want to do. And what OTIO is trying to do is hit this Goldilocks point where it works well for the pipeline integration and the automation use cases that are most common in film production. So there's another thing that I like to do. I like to come back to these 3 things. And those other formats are really focused on this interchange format for communicating things. And all the power in those formats just comes from how well implementers adopt that specification, right? But OpenTimelineIO actually has these other 2 things which are working really strong for it. You can, if you ignore the interchange format section of it, you can pick up OpenTimelineIO, start reading EDLs using those adapters, manipulate them using the API and the data model, and spit them out to other formats using those adapters. So let's get to the critical stats of OpenTimelineIO. It's a Pixar-hosted open source project. It's driven by real-world use cases that they've had in their production. It contains contributions from a lot of visual effects and animation studios, and we're starting to get industry adoption from vendors. It's been in development since 2016, and about a month ago, it released public beta 10. So it's had some iteration time, some time to bake in the oven. It currently ships as a Python API. There's a C++ API that's in a branch that anyone can pull down and start to tinker with. It includes adapters for all the formats we previously described. And more adapters can be implemented very easily using a plugin system. So if you have a studio-specific use case, that's fine. You can create an adapter for that. So let's take a quick look at the data model. It's a bit hard to read. At the top, you have a timeline. A timeline has a stack of tracks. And then each track has a, let's see if I can remember. Yeah, each track has a list of clips in it. And you can stuff transitions between those clips that describe how they overlap with one another. And then finally, clips refer to media references, which tell you how to locate the actual asset to apply these time decisions to. This is what a clip looks like in the OTIO serialization format. Its serialization format right now is just using simple JSON so that you can pop it open and see what's going on in there. And most objects in OTIO looks pretty similar to this with a few expanded fields. But if you look at the timing model within here, you'll also see that it's using time fractions. So you have a rate. In this case, it's the frame rate of the content, 24 frames per second, and a value. And so in this case, that value ends up being a frame number. And here's a minified version of what one of those media references look like. So you can see there is a name for that and a target URL describing where that essence could be located on disk or where it was located when this was authored. But there's this other blob right down here, which is a metadata blob. You're actually able to, in OpenTimelineIO, at just about every object in the hierarchy, insert arbitrary metadata. So in this example, I have an NFLX, Netflix, metadata namespace. And in there, we can punch in an external ID, which is one of the IDs we use, and a movie ID, which is another ID we use. And any of our tools down the pipeline can then pick those up. And rather than having to rely on tearing apart file paths and hoping that there's good naming convention, we can just go ask the database what the asset is that we should be working with. So what does the code look like? Hopefully this is visible. This is a script that walks through the EDL to find which clips are used for which time ranges. So this is the bulk of the code I used to generate that earlier slide where I showed you what was used within the trailer. It starts with opening the timeline and deserializing it from disk. And then it steps through each track, and within each of those tracks, it visits each clip within them. It goes and asks the metadata object for the Netflix metadata, and then further asks the Netflix metadata for the movie ID. And then finally, it gets the used time range from the clip and stashes that in a dictionary for later reference to return back. Pretty simple. One of the other things that's really useful about this is that there's a viewer application that lets you pop open any EDL format that OTIO supports. And this application is actually what I screenshotted to show you that earlier example as well. So what I want to do is I want to pop out and show you an example of using that OTIO viewer app with the HLS adapter that I had written. So in here, we'll pop over to the terminal. So let's start by just doing, I'll show you in this directory here, what I've done is I went and I grabbed an Apple BitBoop HLS manifest and localized it here. And so you see there's all the audio streams and all the video streams as M3U8 files. Because OpenTimelineIO has an adapter for HLS manifests or HLS playlists, I can just do OTIO view, and let's give it prog index, I don't know, v1.m3u8. So we pop it open, and what we do is, since these playlists are actually just expressing timelines, they're expressing map these bytes in this file to this time of playback, you can sort of express that as clips on a track. So you can zoom in and out and select any one of these. It's going to be hard to read, but what is in here is in the metadata blob on that media reference, there's a streaming section, and it actually tells you what the byte count for that segment is, what the what the byte offset of that is, and it tells you the init byte ranges. So what it's doing is it's using all that stuff that isn't inherent to OpenTimelineIO's data model, is putting into this metadata section so that you can read it into OpenTimelineIO, work with it, and then write it back out using OpenTimelineIO to another HLS playlist and carry that information through. And then down here, it's hard to read, but you can see it's an 8-second segment duration. OK, so that's pretty neat. The other thing I did is I took all these and I pre-baked them into an OTIO file. OK, hls.otio. So I baked those all into an OTIO file. And you can see, oh, look, this looks pretty SAP aligned, right? But as you zoom in, you realize, oh, they're not quite all aligned here. There's a discontinuity. So very quickly, if you are having an issue with your HLS playlist, you can pop it open in this utility and start to dig into what's going on and find out, oh, I have 7.1 second and 7.6 second segments. That's why my segments are getting misaligned. Having a visual debug tool like this is extremely invaluable. All right. So, as we move on, OpenTimelineIO is incredibly useful already. It's still public beta software, so you might find that there's some edge cases that aren't well supported. And if you fall into one of those edge cases, that's a great time to get involved. The project's developed in the open using GitHub and a Google Group message board to discuss the design decisions. Also, the community that's supporting it right now are a lot of people working really strongly in the content creation community. Of course, there's Pixar involved, a little bit of Netflix in there, and a number of other visual effects studios. And I want to give a shout out to Stefan and Josh Miner, who are the project maintainers. They create a really inclusive community, and they're really into getting as many people involved, and really, they want to accept all those pull requests and make this thing really strong. So I encourage you to check it out. At Netflix, we're in the process of adopting OpenTimelineIO for a lot of our production pipelines. Also, if you're interested in more, you can go here, or you can do what I always do and just pip install it in your Python projects. So Premiere right now is supported via the FCP XML adapter. And most people that integrate with Premiere tend to use FCP XML as the interchange. So that's the best way. What this is mostly, what OTIO has been focused on for the moment is expressing that timing metadata. There are effects modeled in there. However, designating exactly how those effects should be rendered or how keyframing should be expressed on those effects, that is on the list of things to include. It's being really actively designed right now, so if you have interest in that, we would love to hear from you. I think the initial set of things we'll do is simply lays out a set of really specific effects and how they should be rendered and what parameters should go into them. So I think that will be the initial set of effects that go in, but we're still looking at exactly what the use cases around those look like to make sure we model them really well. It's growing. It's not tremendously widely used, but as we're building more technology on our studio side, it's starting to propagate more and more and more. So our adoption started maybe 6 months ago. So as solutions roll out, you're seeing more and more and more of it come in. Oh yeah, so yeah, that's actually a really great question. So the initial implementation was done in Python because that was the pipeline that's where pipeline developers and film production tend to work. So that was the focus. C bindings were the next step from there once things solidified a bit more, because a lot of visual effects tools are written in C++, and to be able to integrate with those, and then also to be able to appeal to NLE vendors and have it integrate more easily with what they're building, C++ is the answer for their use cases. Another nice thing is that you can bind Python really cleanly to C. You can bind a lot of languages really cleanly to C. So I think if you go into the C++ project right now, there's the C++ implementation, and then there is a set of fully featured Python bindings, and the way they're making sure the C++ implementation works is by running the Python unit test against the C++ bound to Python. And then I think also, just to make sure there's a second language binding against those, there are Swift bindings in there for the moment, because Pixar does a lot of Swift in their story editorial post pipeline. But there's any other number of languages. You could do node bindings for C++. Another thing that I've been thinking about is to get JavaScript bindings. We might be able to use mscripting to build the C++ to something JavaScript can call into. There's a lot of usefulness in having that shared implementation that is able to port around all these places. However, at the same time, ideally, we can make multiple implementations. The file format is going to be an interchange format. So ideally, as long as you can read that, you can do something with it. Thank you, everyone.